In this video, we'll look at asymptotes of rational functions. Many of the rational functions that we'll encounter will have some kind of asymptote. So it will be useful for us to discuss some notation around asymptotes, some definitions, and some observations about asymptotes as it relates to the structure of the rational function. And we'll conclude by doing an example. So first, let's just graph this rational function. So we know that this starts out as just 1 over x, right? That's the base function. It looks like if we say that f of x is 1 over x, r of x equals f of x minus 2 plus 2, which would tell us that r is the base function 1 over x shifted over 2 units to the right and up 2 units. So we'll draw the asymptotes at that point, and we'll draw in the rational function. So that's what this will look like. Now I want to look at the behavior around the asymptotes. So for us to be able to describe this line, this is x equals 2 and this is y equals 2. For us to describe the line x equals 2 as a vertical asymptote, it first needs to meet some particular criteria. So I want to talk about first what the y value of r of x is doing as we approach x equals 2. So, let's start on the really positive side. We're starting on the really positive side, and we're slowly kind of making our way along here. And as we approach the asymptote, what's happening to the y value? The y value is getting really large, right? It's going to infinity. The smaller the number is in the denominator, the bigger the function is. So we might say that as x approaches 2, from the positive side, this is an important piece of notation, if there's a plus in the exponent, quote, quote, of 2, that says that we're starting on the positive side of 2. So we started out here, and then we kind of worked our way in to x equals 2. We didn't quite get there, but we got really darn close. So as x approaches 2 from the positive side, y goes to infinity. And if we were to look down on the other side of x equals 2, of that asymptote line x equals 2, we might say that as x approaches 2 from the negative side, y goes to negative infinity. This is called arrow notation. So this helps us define that x equals 2 is a vertical asymptote. So similarly, we might say that as x gets really, really large, what value y does r approach? As x gets really large, that's how we can read that. X approaches infinity is the same thing as saying x is getting really large. Y goes to what? Y gets to 2, right? The larger that we make x, the smaller the term 1 over x minus 2 becomes, which would leave us with just 2. And then similarly, as x approaches negative infinity, y goes to positive 2. So let's summarize that. The definition of vertical and horizontal asymptotes. The line x equals a is a vertical asymptote of the function y equals f of x if y goes to positive or negative infinity as x approaches a from the left or right. And there are a couple examples here. In the first example here, as x approaches a from the positive side, y goes to infinity. The next one over, x approaches a from the negative side, y goes to positive infinity, and so on. And then the second part says that the line y equals b is a horizontal asymptote if y approaches b as x approaches positive and negative infinity. So notice that in some cases, like this one on the right-hand side, you may actually cross over the asymptote. These cases are few and far between, but you may well encounter one. So that's something to keep in mind while you test values for what's happening between two vertical asymptotes. And the next definition, finding asymptotes of rational functions. So it happens that there are patterns to help us identify what asymptotes are of a particular rational function. For a rational function with a polynomial p that's arbitrarily complex in the numerator and a polynomial q that's arbitrarily complex in the denominator, the vertical asymptotes of r are the lines x equals a, where a is the zero of the denominator. So we're looking at this polynomial down here, which we could, of course, factor completely now that we've done enough reading into that and done enough study into that. So we could find all the points that make all the x values that make the denominator equal to 0. Now, if we compare the degree of the numerator, n, and the degree of the denominator, m, if n is less than m, r has a horizontal asymptote at y equals 0. If n is equal to m, r has a horizontal asymptote y equals an over bm. That's the leading coefficient of p over the leading coefficient of q. And then if the degree in the numerator is greater than the degree in the denominator, then there is no horizontal asymptote. And that's a special case that we'll talk about more later on. So now let's graph a rational function. So we have r of x equals 2x squared minus 4x plus 5 over x squared minus 2x plus 1. First thing to identify is any vertical asymptotes. And we can do this by factoring our rational function. So if r of x equals 2x squared minus 4x plus 5 doesn't actually factor, but x squared minus 2x plus 1 does, and that's just x minus 1 squared. And remember, we get vertical asymptotes for every x value where the denominator equals 0. And there's only one where that's true. So vertical asymptote in this case is just x equals 1. Because when r of 1, we have something over 0, which that's uncool. We don't want to deal with that. Now let's find the horizontal asymptote. So, like we just talked about, we can look at the leading coefficient of the polynomial in the numerator and put that over the leading coefficient in the polynomial of the denominator. And that will say that our horizontal asymptote is y equals 2 over 1, which equals 2. And again, the intuition is if we multiply the numerator by 1 over x squared and the denominator by 1 over x squared, we would end up with 2 minus rational functions over 1 minus rational functions, where those rational functions go to 0 as x gets large. All right, so we'll plot this. Maybe have something like this. We'll call that 2. And we'll call that 1. Now at this point, we could test some values. We could rely on some knowledge that we have. 2x squared over x squared, I have a feeling that's going to look a lot like just 1 over x squared, right? But if you test the values starting just before and just after x equals 1, you would find that we have something that looks like this. Of course, more often than not, we'd expect a little bit more precision than this, but this is just to get you all thinking in the right direction. Now, from our graph, we can get the domain and range. The domain is what? All reals except for 1. And the range is what? The range is strictly greater than 2. So that would be 2 to infinity. And I'm kind of mixing my notation there. I've got set builder notation and interval notation, but just to make it clear, the domain and range of this particular function.